Now that we've taken a look at ionic compounds, it's important for us to look at the other class of compounds, covalent compounds. So when we look at covalent compounds, unlike ionic compounds that are attracted together by an opposite charge, these types of compounds are formed by a chemical bonding of non-metal atoms to other non-metal atoms. So what we see is that because neither non-metal atom is strong enough to steal electrons away from the opposite atom, instead, they have to share an electron pair, usually one electron from each element. What I remember is that covalent compounds have to cooperate, and they do so by sharing their outermost electrons. In doing so, they're hoping to achieve what we call the octet rule, which states that atoms will gain, lose, or in the case of covalent compounds, share electrons in order to acquire a full set of valence or outermost electrons. That will fill their outer energy level. We'll talk more about what that particular piece means when we look at electron and orbital theory. That won't be till after the mole. But for right now, in most cases what we see is that means that there are 8 electrons in their outer shell or orbit, or we'll learn later orbital, and that means they're isoelectronic with an inert gas. When we talked about isotopes, I told you already that iso as a root means the same. Isotopes are the same type of atom, they just have a different mass. So isoelectronic means that they have the same iso electrons, so they have the same number of electrons. When it comes to naming covalent compounds, there's a very few simple set of rules. The first is that the more metallic non-metal atom is the one that gets listed first, because it's the one that loses its electron most easily. In other words, it has the lower electronegativity. Electronegativity is a measure of how strongly an electron holds onto or attracts an electron into its nucleus. What we see is that the most electronegative element on the periodic table is fluorine, where the least electronegative element on the periodic table is cesium. So the further you are from fluorine, the less electronegative you are, and the more metallic. We do have a table on the back of our periodic table which gives you values for electronegativity. The lower the number, the lower its electronegativity. Generally, as a trend, what we see is the element further to the left in a row is more metallic, so it would go down first. Also, the element further down in a group or family is less electronegative, more metallic, and so it would go first. So when we look at a compound containing nitrogen and oxygen, the nitrogen is further to the left than the oxygen, and so it would go first, for example, in nitrogen dioxide. In contrast to that, when we look at a compound containing sulfur and oxygen, sulfur is further down the table than oxygen, and so it would be listed first. The second thing we need to know is that because the atoms are sharing electrons, there are no charges to balance. And because of that, atoms can possibly share electrons in more than one way. To tell how the atoms are sharing or in what ratio the atoms are sharing their electrons, we have to use prefixes to say how many of each element are there. Now you have to memorize this list, but here are a couple of quick tricks for you. Mono, a mono as a meaning means one. So mono means one. Die, you know that you normally play games with two dice, and that means two. Tri, everyone knows, is a tricycle. Tetra is the one that's kind of tricky, but it's not if you remember the 1980s, 1990s game, which involved four-sided figures, or in groups of four, Tetris. So tetra means four. Penta, the pentagon in the States, has the five-sided building. Hexa, hepta, and octa are ones that you just have to remember, but people remember an octopus has 8 legs, so that's okay. Now, what we always do, just like in an ionic compound, is change the name of the second element to become an IDE. We keep the first syllable, and the rest drops off to become an ide. So oxygen becomes oxide, Nitrogen becomes nitride, sulfur becomes sulfide, and chlorine becomes chloride. When we use the prefixes on covalent compounds, that's because elements have no charges to predict their chemical formula. That's why we don't use them ever in ionic compounds, because ionic compounds have ions, and ions have to balance out their charges overall. So when we look at changing, let's do a couple of examples here. The first thing I always do is write down the elements' names. So the first element, let's just get my pen ready. The first element gets its name written down unchanged, just like in an ionic compound. So sulfur. And the second element, you already know, becomes an ide. So this is oxide. When we place the prefixes on, the first element only gets a prefix if it is not a 1. So in this case, we have sulfur, but there's only one of them, so it doesn't get a prefix. The second element always gets a prefix. So there's 2 oxygens, so this becomes dioxide. Looking at the second example, again, we're going to write down the elements' names first. So this is phosphorus. Its name isn't changed because it's the first more metallic element. The second element's name always becomes an ide, so again, it's still oxide. Now we look and see whether we have to apply prefixes. Do I need a prefix on the first element? Yes, I do, because it's other than 1. So I need to put a prefix of di to show that there are 2 phosphorus. The second element, regardless of how many there are, always needs a prefix. So this one, for 5, is pentoxide. If you put pentaoxide, it would be totally acceptable. Okay, now let's look at how to go from the names to the formulas. And this way, I happen to think is just a little bit easier. So the first one I look at is carbon. It's a C for carbon. And it doesn't have a prefix on the first one, meaning that there's just a 1. Chemists are lazy, and we almost never write 1s in because writing the symbol implies that there's 1 there already. Looking at the oxide, remember that that means an oxygen, and this time it's got a prefix of di, so it is 2. This is CO2. Second example, we have dinitrogen. So again, this is nitrogen. And this time it's got a prefix, so it's not a 1. It needs to have a subscripted number. And di represents 2. Oxide again is an O, but this time it's tetra. Tetra, remember, goes back to Tetris, so that means it's a 4-sided 4-oxygen compound. So what we're going to see next is that we're going to do some practice of this in class, and then we're actually going to move on in class next day and talk about how we name acids, and we're also going to look at a specific group of other compounds called hydrates, and that will finish our look at pure substances. Early next week we're going to start looking at mixtures and how we can distinguish between and separate mixtures.